Learning target 5, we're going to graph linear inequalities. And in learning target 4, we graphed a linear equality. So we're already used to graphing with slope and y-intercept. We're just going to make another connection with graphing an inequality. So the first thing we did in the bell work was to remind ourselves what it looks like in one dimension on a number line. So graphing the answer, x equals 2. Go ahead and mark both of these down real quick. Graphing x equals 2 simply looks like a solid circle at 2 to signify x equals 2 is the only thing that works. But when we go over to x is greater than 2, we start thinking, all right, well, the first number, let's see, 2 does not work. X equals 2 is not greater than 2, so we signify that with an open circle. But any number bigger than 2, 2.1, 2.01, 3, 4, 5, 6, 7, 8, anything bigger than 2 works, so we shade to the right. All right, so now we're going to connect that to graphing in 2 dimensions. So our first example is graphing x plus 3y is less than 6. So our first step is to take x plus 3y is less than 6 and change it to equals. What we're essentially doing is this. We are thinking about x value 2. We're thinking about, does 2 work? We're trying to find out where 2 is on the line to decide, do we shade left or right? So anyways, I know that's really conceptual this early, but let's keep going. Graphing this in slope-intercept form, we'd subtract x to both sides. This is learning target 4 if you need to go back and look at it. Divide by 3, so y equals negative 1/3 x plus 2. So the slope is negative 1/3, the y-intercept is 2. So we go to y-intercept 2, down 1, right 3, down 1, right 3, or up 1, left 3, up 1, left 3, etc. All right, so the boundary line is there. Now, be careful. We're not going to grab a ruler and connect the dots just yet because we need to think of something. The less than is saying that the points on the line won't work. And so to prove that, I'm just going to pick one, the point 3,1. It's on the line, the point 3,1, and plug it in. 3 plus 3 times 1 is less than 6. Plugging 3 in for x, 1 in for y, we get 3 plus 3, 6 is less than 6. That's not true. 6 is not less than 6. So unless it has the equal to underneath that less than, it'll never be true. So what did we do in one dimension? We used an open circle when 2 is greater than 2, when that 2 does not work. So in 2 dimension, we can't put a bunch of open circles, so what we do is we put a dotted line just to say that every point on the line does not work. So I'll grab the dotted line feature and do the best I can to connect those with a dotted line and then draw the arrow going the other direction as well. All right, so that's step 1, putting the dotted line to say those points on the line don't work. Well, back in one dimension, that was like putting the open circle. There was still a bunch of points that do work, a bunch of values for x, so there was some shading. So step 2 in graphing a linear inequality is figuring out where the points are that do work. So we're going to test one. I like testing the origin, 0, 0. If it's not on the line, you can test it. So I will test 0, 0 in the original inequality, x plus 3y is less than 6. I'm going to plug a 0 in for x and a 0 in for y. When I do, I get 0 plus 3 times 0 is less than 6. I get 0 plus 0. I get 0 is less than 6, a true statement. Which means that I should shade the side of the line that has the point 0, 0 because because that point works. Furthermore, every point on this side of the line will work. Just to prove it, I'll pick a more random point just to prove that it does work. Let's try 4, negative 2. It's in our shaded region, 4, negative 2. So let's see if 4, negative 2 works. And it will because anyways, let's try it. 4 plus 3 times negative 2 is less than 6. 4 minus 6 is less than 6. Negative 2 is less than 6. Again, true. We could try or plug in as many points as we would like on this side of that line, all that we shaded here, and every one of them will work. So that's our final answer. So a few little conceptual yes-no questions. Does the point 2, 3 work? Answer would be no, because it's not in our shaded. Does the point 1, -5 work? 1, -1, 2, 3, 4, 5. Don't have to plug it in. I can just look at the shading. Yeah, it works. And then the final one, does the point 3, 1 work? 3, 1 is on the dotted line. It doesn't work. Well, we already plugged it into C. I should have picked a different point. How about 0, 2? Does it work? Again, it's on the dotted line. The answer would be no. That's why we used a dotted line. Sorry, I had to pause the video there. And so that concluded our first question, graphing that inequality. So let's try another one. 4x minus 2y is less than 6. First, we're going to graph the related boundary line by graphing 4x minus 2y equals 6. So subtract our 4x, subtract 4x, negative 2y equals negative 4x plus 6 divided by negative 2. So y equals negative 4 divided by negative 2 is positive 2, and 6 divided by negative 2 is negative 3. So start by graphing the y-intercept negative 3. Then graph the slope 2, up 2, right 1, up 2, right 1, and so forth. Down 2, left 1, down 2, left 1, down 2, left 1. All right. So our boundary line is at least the points are graphed or plotted. We need to look now at the inequality sign. It says less than. I want to change that. I don't like that. I'm going to actually change the original problem. I want it to say less than or equal to, because I want to do a different kind of question than we did in the first one. So if it's a less than or equal to, the points on the line will work because it has equal to. Let's prove it. Let's take the point 2, 1, for example. 2, 1, and plug it in. 4 times 2 minus 2 times 1 is less than or equal to 6. That would give us an 8 minus 2. 8 minus 2, 6 is less than or equal to 6. That's true. So there's a point on the line, and it works. And it gave us 6 is less than or equal to 6. It gave us the equal to version. Because it has the equal to in the original problem, now that I changed it, every point on that line will work, so we will connect it with a solid line. Just like if we were graphing in one dimension, back here, if this had been x is greater than or equal to 2, we would have used a solid circle. So solid circle, solid line. All right, now, that should have been a blue line, but we can deal with that. Step 2, test a point that's not on the line, so we can decide whether we shade on the left / above the line, which is really above, or on the right / down, which is really down. But let's test a point and see if it works. I like testing the origin if it's not on the line, and once again, the origin is not on the line, so we can test it. 4 times 0 minus 2 times 0, is that less than or equal to 6? 0 minus 0 is 0. So yes, 0 is smaller than 6. That's true. So we can shade the side of the line that contains the origin. So that would be shading all of these points. And adjust that over a little bit. And then we have all of our solutions that could possibly work for the original problem, 4x minus 2y is less than or equal to 6. So we asked a few yes-no questions. The first one, is the point 2, 10 up here in the solution set? Yes, it's in the shaded area. Next one I asked was, is the point 10, -1 over here? Is it in the solution set? No, we don't have to even plug it in. We can look at our picture to tell. No, 10, -1 is not in the shaded area, so it's not going to work. Then finally I asked the question, does 3, 3 work? And it happens to be on the line. This time it's a solid line. So yes, but even without plugging it in, we can tell that the point 3, 3 would work. All right, now the final problem. This is the really should be taught the day after, but since I'm recording this video, I'll go ahead and do the shortcut version as well. I want to show how to graph this without testing a point, because there is a little shortcut. And once you understand the step 2 testing a point, step 2 testing a point, and you really understand why you're shading that side, it's okay to use the shortcut because you still understand what the shading means. So anyways, how to do this without testing a point. First, isolate the y like you would putting it in slope-intercept form, except keep it a less than, and follow your rules of inequalities. Subtract 4x, subtract 4x. So we have negative 2y is less than negative 4x plus 6. Divide by negative 2. So y, and if you divide by a negative, the less than has to be flipped to greater than to keep that inequality true. Negative 4 divided by negative 2, positive 2 times x, and 6 divided by negative 2, negative 3. So our slope is 2. Our y-intercept, negative 3. The fact that this is a greater than is telling us two things. A greater than tells us two things. One, dotted line, because it does not have the equal to. That one we kind of already were learning or knowing. But if it says y is greater than 2x minus 3, the question's kind of asking, where are the y values that are bigger than this line? And if you think about y values getting bigger, and you're looking at a xy axis, y values get bigger as you go up. So this is telling you to shade up. Now this is kind of a little trick, and it only works if y is on the left side. Y is bigger than the line. But again, if you understand testing a point, it's okay to use that to shortcut the process. So put it all together, and y-intercept's negative 3. Slope is up 2, right 1, up 2, right 1, up 2, right 1, and so forth, down 2, left 1. Grab a ruler. It's dotted, so we will take a ruler and make a dotted line. And according to this, we'll shade up, shade above. So above that line would be up here. So there's the shortcut to graphing an inequality in slope-intercept form. And that concludes Learning Target 5.